Welcome to Chem Time.
Hello viewers, welcome to the YouTube presentation. Today's presentation is about measurement of pressure differential using manometer. I start the presentation by discussing the applications of use of manometer in two of the laboratory experimental setups. These two experimental setups are available in chemical engineering, mechanical engineering, civil engineering, agriculture engineering, and petroleum engineering laboratories. The experimental setups are: one is pipe friction experiment, the second one is orifice and venturimeter. The manometer is highlighted in both the experimental setups. Coming to the types of manometer, the manometers are categorized into single column manometer, U-tube manometer, inverted U-tube manometer, inclined manometer, and two-fluid manometer. U-tube manometer deserves its name mainly because of the shape of the tube that is being used for measurement of the differential pressure. I remember one of my students when we were discussing this pressure measurement using U-tube manometer, one of my students, Mr. Gopal, came up with the antenna pipe and asked me whether this resembles a U-tube manometer. I really appreciate his intuition on that particular day through this presentation. Now, in this presentation, I am going to discuss about single column manometer and U-tube manometer. The procedure that is going to be adopted is we derive the equation for the pressure difference and take a numerical problem and substitute the values given in the numerical problem to have a feel of the pressure or the pressure differential. In single column manometer is meant for measuring gauge pressure by measuring the rise of liquid height in small diameter tube when the pressure is applied on the large diameter tube. So that implies single column manometer contains a small diameter tube connected to a large diameter tube, and the small diameter tube is exposed to atmospheric pressure. Now, the problem that is given in JNTU-K for mechanical engineering in the year July 2023 is a single column vertical manometer is connected to a pipe containing oil of specific gravity 0.8. The area of the reservoir is 70 times the area of the manometer tube. The reservoir contains mercury of specific gravity 13.6. The level of mercury levels in the reservoir is at a height of 250 mm below the center of the pipe, and the difference of mercury in the reservoir and right limb is 450 mm. Find the pressure in the large diameter pipe. Now, when we solve problems related to the manometer, the fundamental principle that need to be understood is the pressure is same at all points in the same horizontal level within a homogeneous incompressible fluid. In this particular case, the pressure at x and x will be same. Similarly, the pressure at y will be same. Since when pressure is applied, the liquid level in the reservoir drops and the liquid level in the smaller pipe rises, the drop in volume of liquid in the reservoir will be equal to rise in volume of liquid in the manometer pipe. So that is capital A into delta H is equal to small a into H2, where delta H is the drop in level of the liquid in the reservoir and H2 is the height of the liquid in the smaller pipe. And capital A and small a are area of reservoir and area of the pipe respectively. As a result, delta H will be equal to A by A into HT. But the reference line is taken as YY, where the pressure at Y becomes equal to the pressure at Y dash. And this is the principle that is being adopted for calculation of the pressure differential for any manometer. The pressure in the reservoir will be equal to pressure in the manometer. So pressure in the reservoir will be equal to density of the fluid in the reservoir, that is denoted as rho reservoir into G into H1 plus delta H plus PA. PA is the pressure in the reservoir. the pressure of the liquid in the reservoir. And the pressure at Y dash will be equal to, since it is influenced by atmospheric pressure on one side, atmospheric pressure, this is the dynamic pressure, plus rho m pipe, that is density of the liquid in the manometer pipe, into G into H2 plus delta H. The atmospheric pressure value is 101,300 newtons per meter square. So with this, the pressure at Y dash will be 101,300 plus rho m pipe into G into H2 plus delta H. If this 101,300 is eliminated, the pressure PA that is going to be calculated will be gauge pressure. So now we can get an expression for PA as 101,300 newtons per meter square plus delta H into G to rho m pipe minus rho reservoir plus G into H2 rho m pipe minus H1 rho reservoir. Now, if the given numerical values are substituted in this particular equation, rho m pipe is 13,600 kg per meter cube, rho reservoir is 800 kg per meter cube, A by A is 1 by 70, H2 is equal to 450 meters, that is 0.45 meters, H2 is equal to 250 that is 0.25 meters. With this value substituted in the given equation, the pressure in the tank is 160122, that is 160 kilopascal. The second problem is using a U-tube manometer, and it is given as one leg of mercury U-tube manometer is connected to a pipe containing water at a gauge pressure of 100 kilopascal. The mercury in the leg stands 0.75 meters below water. The mercury in the other leg is open to air. So here the pressure is atmospheric. The density of water is 1000 kg per meter cube and that of mercury is 13,600 kg per meter. These values are shown in the figure. What is the value of height H2 that is shown in the figure? Now, as I mentioned, we have to write the pressure equating the pressure at two horizontal planes, and in this case the two horizontal planes are x and x dash as shown in the figure. Pressure at x dash is equal to pressure x dash. The pressure at x becomes the dynamic pressure 100 kPa plus the static pressure. So the pressure at x is equal to 100 kPa, that is gauge pressure, plus 101.3, that is absolute pressure, that is 201.3 kilopascal. With H1 is equal to 0.75 meter, density of water 1000 kg per meter cube, G is equal to 9.8 meter square. The pressure at x dash will be x is equal to rho water into G into H. With this, the pressure at x will be equal to 1000 into 9.8 plus 0.75 is equal to 7350, that is 7.35 kilopascal. So the pressure at x will be equal to 200.3 plus 7.30, that is 208.6 kilopascal. The pressure at x becomes x dash 101.3 kilopascal because the other side is open to atmosphere, plus rho mercury into G into H2, where H2 is the height that need to be measured and rho mercury is the density of the mercury. That becomes 101.3 plus 13,600 kg per meter cube H into H2 into 9.8 meter square. Now the pressure at x becomes equal to the pressure at x dash, and based on this principle 208.6 kilopascal will be equal to 101.3 kilopascal plus 133.28 H2, which gives H2 is equal to 0.8 meters. In the subsequent presentations, we'll be discussing about the inverted U-tube manometer as well as two liquid manometer. With this, I conclude my presentation. Thank you.
Request you to like, share and subscribe my channel.